upload it on YouTube, and that is easier to embed. Okay. Okay, so today, so last 4 lectures we were talking about randomized algorithms. Yeah. So today we will start on a new topic. Yeah. So we will start on quantum computing. Yeah. So yeah. Yeah. So yeah, before I start on this, I should also say some caveats. So I haven't done any research work on quantum computing. Okay, so I have attended a course. So my idea of quantum computing is also very basic. Okay, but I will give you enough references which yeah, I mean which are more interesting. Yeah, which gives more insights into this. Yeah. So it's also natural to look at quantum computing after randomized algorithms. Okay, so it is really the next extension of computing. Okay, so we start with deterministic algorithms, then we looked at randomized, and then quantum mechanics is kind of the next level of computing. Yeah, and that's yeah. Okay, so what is quantum computing? So yeah, so as you know, so you have done your double slit experiment in your +2 and so on, right? So you typically do this experiment with yeah, 2 slits of light, and you see that okay, by particle nature, okay, the pattern should be something, and wave nature the pattern should be something. There is an interference pattern that should come up, and you discover that okay, yeah, light behaves by this wave nature, and there is this interference pattern, yeah, forming. Okay, so physicists yeah, looked at how electrons behave or photons behave, and they said that the only explanation yeah, to yeah, which is consistent with all the experiments that you can do, yeah, requires that these particles, whether it is photons or electrons, are in a quantum state. Yeah, and the quantum state requires complex numbers and everything to represent, and only, I mean, that kind of yeah, I mean, only describing a photon or electron with a yeah, that kind of mathematical setup, it was they were able to explain all the experimental results. Okay, yeah, so you have any other comments about quantum computing? Anything else you found out about quantum computing? Okay. Yeah, so so in the early 1980s, okay, in 80s, yeah, I mean, after quantum computing, people and all, they thought okay, maybe you should also apply quantum principles to computing also. So it was initially, it was in the 80s, it was proposed by Feynman. So I can give you the reference, but yeah, it was proposed by Manin, Feynman, and Benioff. Okay, so in the 80s they proposed okay, you should make use of quantum computing for computing also. You should look at yeah, quantum mechanics way of solving things. That was in the 80s, so it is a very novel idea. It's not very old or anything. In 80s only people started even thinking about it. Somebody even yeah, thought about okay. Now in 85, yeah, so somebody yeah, the person named David Deutsch proposed a quantum Turing computer. It's an analog of a Turing computer for the quantum world. So 80s, yeah, Feynman, yeah, they proposed that we should do quantum computing, and in 85 Deutsch yeah, proposed the universal I mean quantum Turing machine. Yeah. And yeah, so after that yeah, people started getting interested. Okay, so I mean the main interesting discovery in this area was Peter Shor. So this happened maybe in the 90s, yeah, 94. Yeah, Peter Shor discovered there is a fast quantum algorithm, yeah, to factorize a number. factorize a composite number, yeah, and also to find what is called discrete logarithms. Now, this was a shock to everyone. This was a shock to everyone because all the cryptographic tools that is even now used, yeah, kind of assumes that these two problems are really hard. We don't have a polynomial time algorithm in a Turing machine for factorization or discrete logarithms. Okay, for these two problems we don't have polynomial time algorithms for these, but Peter Shor discovered a quantum algorithm. If you have a quantum Turing machine, yeah, you can actually do this in polynomial time apparently. So, if you have a question, please speak out because I have too many windows on my screen. What is a discrete logarithm? We will come to it at a later point. It is a discrete version of logarithm. Let us say you want to take powers modulo some prime, yeah, and given a power you want to find the initial number, yeah, and yeah, that is what kind of or find the power, yeah, that is what discrete logarithm is. It is exactly the normal logarithm, but when you do modulo p, okay. So, and the encryption protocols like RSA and everything, use these kind of functions. So, if you actually can solve this in polynomial time, you can actually decrypt the message from the public key and everything, yeah. So, it was yeah, if you have a quantum computer, all your encryption and everything gets broken, okay. So, yeah, okay, just a second. So, please speak out because I cannot see your chat messages because I have too many windows in my screen. So, it is better if you speak out, yeah, and we can have a conversation. Okay. So, yeah, so this was a like dangerous discovery by Peter Shor, okay. But happily we are still using all this because we still do not have a big enough quantum computer. The biggest quantum computer I think has been able to factorize 15 is equal to 3 into 5 or something like that, okay. So, right now we do not have really big quantum computers. Even the news that you hear about quantum computer, they are not able to solve, they are only able to solve certain types of problems, not really the factorization, okay. So, there is it is very difficult to come up with gates and everything to do quantum computing reliably, but it is an emerging area, we do not know what is going to happen in the future, yeah. So, it is very important that we have a theory for it, yeah, and yeah, okay. So, so a theory for quantum computing has multiple consequences, okay. One, it tells you about, okay, what are the problems which are really hard even in the quantum computing world, yeah. Can we solve NP problems in using quantum computer? Maybe we do not know, yeah. So, all those are interesting questions. Also, if you actually learn quantum computing from if you look at quantum mechanics from a computer science point of view, and certain questions in quantum computing also results in very big results in physics. It actually yeah, for example, there are computer scientists who have like discovered quantum computing yeah, theorems which will have consequences to black holes and everything. It is amazing, okay, yeah, and yeah. So, people study this basically for two reasons, because soon we might have quantum computers, and then we should have quantum computing algorithms as well as quantum computing hardness results. Also, this also throws light into the physics itself, okay. So, it is a highly interdisciplinary area, quantum computing, okay. But we will be mostly focusing from the computer science point of view, okay, because I do not know much physics, yeah. So, we will be purely looking at some quantum computing algorithms, yeah, for which classical computer algorithms are yeah, we do not know, or it is exponential time, yeah, and that is those kind of algorithms we will be looking at. So, in this lecture we will basically give out some definitions. Yeah, we will be seriously looking at algorithms from the next lecture onwards. Yeah, but today I will be introducing the basic definitions and terms. Okay. Yeah, is there a question? Okay. Yeah, so let me get started. Yeah, so first thing that happens in quantum computing, yeah, the first principle, okay, one of the first principles in quantum computing is the principle of superposition. Yeah, so so suppose you are looking at an electron, okay, and in which orbit it is, yeah, revolving around the nucleus. Yeah, so I mean, if you are working with quantum mechanics, you cannot say that, okay, it is in this particular orbit or that particular orbit. Yeah, there is some it is in a superposition of states. That's what people say. Yeah, a quantum mechanical object is in a superposition of states. It is not in a single state. Every classical object is always in a single state. Yeah, suppose the states are 0 to k minus 1. These are some states of an object. Yeah. For example, a bit has two states, 0 or 1 state. Yeah, so a object could have k minus 1 k states, and a quantum mechanical object will be in a superposition of the states in general. Yeah. So the way you write it in quantum, I mean in this field is like this. Yeah. So if you look at this particular thing, yeah, there will be k minus 1 of this, and then there is numbers alpha 0 to alpha k minus 1. And this alpha 0 to alpha k minus 1 are actually complex numbers. Yeah, they are complex numbers. Yeah, yeah. And yeah, so one way to think about this is basically the 0 thing. So another way to think about this is just as a vector. This is a k dimensional vector. Yeah. So just a k dimensional complex vector. It's a, and basically the way you should think about this 0 to k minus 1 is essentially 0, this symbol basically represents the standard basis, the first standard basis, and similarly k minus 1 is 1 in the last. Yeah. So I mean, yeah, so yeah, alpha 0, alpha 1 to alpha k minus 1 is basically the coordinates of this particular state in the standard normal basis. Yeah, in the standard basis. Okay. So yeah, whenever you talk about quantum computing, your state will be represented by leads. Yeah, somehow this makes sense, and this they are able to explain various experiments if you assume this way. Okay. Yeah. Okay. So now, so these alpha i's are called the amplitudes. They are complex numbers and they are called the amplitudes. Yeah. So suppose you have two particles. Yeah, suppose you have two particles. Yeah. Suppose there are two particles. Yeah, these are quantum particles. They obey quantum mechanics. Yeah. Then how do you represent the state of them? Yeah. So yeah. So yeah. So the first particle could be, let's say, in n states. Yeah. First particle is in n states. So there could be 0 up to n minus 1. Yeah. So it will be in a superposition of n states. Yeah. The second particle, let's say, is again m states. Yeah. I mean, the second particle can have m states and the first particle can have n states. Yeah. Classically n states and classically m states. Yeah. But quantum mechanically, they can have, it's in a slightly more complicated space. So let's think about this particular space, yeah, as this is typically called a Hilbert space. Whenever you have complex numbers, okay, it's called a Hilbert space. Okay, so let's say you have a Hilbert space HB, and you have a Hilbert space. So let me call this HA and HB. So the combined state, yeah, is going to be a tensor product of the Hilbert states. So HAB is HA tensor HB. Yeah. So how does a state in the tensor product space looks like? Yeah. So yeah, in the individual space, a state look like this. Yeah. So for this individual particle, a state looks like this, but in the tensor product space, yeah, the state looks like yeah. So you take the tensor product of all pairs of basis vectors, yeah, tensor product of all pairs of basis vectors, yeah, and yeah. So in what is the dimension of the combined Hilbert space?
It would be Nm.
Yeah, it is n times m. Yeah, so the dimension is n times m. Why do we say the dimension is n times m? Because a state like this requires n times m complex numbers to represent. There is gamma ij, for every I and j there is a gamma ij. So there are n times some complex numbers you need to represent the combined state. Yeah. So yeah, so this is called yeah, these are called tensor products. So when you have multiple particles, you will basically yeah, take the tensor product. Now yeah, so let's look at some qubits. Okay, so qubits are basically the analog of bits, but in the quantum mechanical world. Yeah. So yeah, a qubit, yeah, is a particle which has two states, two classical states. Yeah, the classical states are 0 and 1. Yeah, but the quantum mechanical state will be a superposition of this. Yeah, so this yeah, belong to C squared. There are two complex numbers to represent a qubit. Yeah. Hello, can you hear me?
Yeah,
Yeah,
yeah, I can hear you.
sorry, there was some disconnection in between. Okay, let's continue. Okay, yeah, so we were talking about qubits, and yeah, qubits is basically the, yeah, there are two classical state, but the in quantum mechanics you can have it as a superposition of those. Suppose you have two qubits. Yeah, so now yeah, your you will have alpha 0 0 0 0 plus alpha 0 1 0 1 plus alpha 1 0 1 0 plus alpha 1 1 1 1. Yeah. So this 0 0 is basically is essentially the tensor product of 0 and 0. Okay. Yeah. So yeah. So if you have 2 qubits, then there are 4 classical states, and yeah, in quantum computing the state could be a superposition of these. Yeah. So there is 4 complex numbers involved. Okay. Yeah. Now yeah. So now one way to get yeah a state of a 2 qubit system is to take the tensor product of individual states. Okay. So let us say you have 1 qubit in this state, yeah, and you have another qubit in this particular state. So you have 1 qubit in this state and another qubit in that state. Yeah. So what is the combined state?
So it would be like alpha 0 beta 0 into 0 0 plus alpha 0 beta 1 into 0 1 plus alpha 1 beta 0 into 1 0 plus alpha 1 beta 1 1 1.
Yeah. Yeah. So yeah. So this seems reasonable. Yeah. Now yeah. So this is the combined state. Okay. Now let me give you another state, okay, of the qubits. Okay. So let us look at this particular state. Yeah. So this is a state in which yeah, both the qubits are in. The combined state is this. This is a valid state, no? There is no problem with the state. It's a valid state. Yeah. Now can you write it like this? Can we write it? Can this be written? As product of individual states. Can you do that? Is the question clear? Yes. 2 qubits is in this state. It's a valid yeah, state according to yeah, superposition. Yeah. Can it be written as the product of individual states? Yeah, I want somebody to make an attempt at least.
If we had done that, so let's say we had said that we can write it as alpha 0. So let's say we could write it as the two distinct things. Then we'd get like 4 equations. So we'd get alpha 0 beta 0 equal to 1, alpha 0 beta 1 equal to 0, and alpha 1 beta 1 equal to 0, and alpha 1 beta 1 equal to 1.
Yeah. So alpha 0 beta 0 has to be 1 by root 2, alpha 1 beta 1 has to be 1 by root 2. Yeah. And
yeah,
these two has to be 0. Is this equation satisfiable?
You can have a product of two terms, and once it will be equal to half, and once it will.
No, if alpha 0 and beta 0 product is 1. Yeah. So both of them are non-zero. You agree? Both of them has to be non-zero.
yeah.
But they are complex numbers. Okay. These two are again yeah, non-zero complex numbers. Product is 1. Yeah. Now can you have complex numbers? Yeah, I mean such that these two equations are also satisfied. Okay. You can spend some time.
You can multiply. Yeah, you can multiply the first and the last term, and you can multiply the second and the third term, and both of these should be equal, but you get them as unequal.
Yeah. So, as Prajwal said, if you spend some time on it, you will realize that you cannot find alpha 0, beta 0, alpha 1, beta 1, yeah, which can be written like this, such that this is achieved as a tensor product. Yeah. So, states like this, which can be when you take the combined state of 2 qubits, yeah, if it can be represented as a tensor product of individual qubits, then it is called unentangled. They are not they are tensor product, essentially they are independent bits. So, the one way to think about this is in terms of distributions. Yeah. So, you have one bit, you have second bit, you have a joint distribution, maybe the 2 bits are independent, then the joint distribution is just the product of the individual distribution. That is what is happening here. Yeah. And sometimes the joint distribution depends upon both the bits, I mean, they are not a product of the individual marginals. Yeah. And yeah, so this state is like that. So, this state we call a entangled state. Okay. Yeah. So, states yeah, when you have multiple qubits, so they can be unentangled, in which you can write it as individual tensor products, and they can be entangled, in which yeah, they might mean there is no way to write it as a tensor product. Yeah. Let us look at an example. Yeah. So, suppose you have n qubits. Yeah. You have n qubits. Yeah. Suppose they are unentangled, all the n qubits are unentangled. How many complex numbers you need to represent it? How many complex numbers you need to represent n unentangled qubits?
2 raised to the power n.
Why 2 raised to the power n?
So if it's unentangled, you can write it as a tensor product of like n states. And for each of them you will need 2.
Yeah. So total.
Yeah, that makes 2n. Sorry.
Yeah.
Yeah, 2n.
You only need 2n complex numbers to represent unentangled qubits. Yeah. But what if it's entangled? It's a general yeah, a general state of n qubits. Yeah. How do you represent, how many complex numbers you need?
Yeah, in this case I think we'll need 2 raised to the power n, because for each of the components we'll need one yeah.
The number of states, the classical states itself is 2 raised to n. Yeah. So, you will have 2 raised to n strings like this inside this kind of, yeah, and so you will need 2 raised to n complex numbers for that. Yeah. So, I mean a general state of n qubits, it is a huge space of complex numbers, 2 raised to n dimensional space. Yeah. But if you are only looking at unentangled qubits, that space is much smaller, only 2n dimensional. Okay. Only 2n dimensional if you are looking at unentangled qubits, but if you are looking at the yeah, bits together, then it can be in a huge, much bigger space. Yeah. And these entangled qubits are somehow the essence of quantum computing. You can do lot of clever things with them. Okay. Because you have a much larger dimensional space, so you can represent much more things with entangled qubits. Yeah. And that is very important in quantum computing, as we will see when we design algorithms. We will create this entangled qubits. Okay. Okay. So, yeah. So, we know how to represent, yeah, I mean a state of a system in quantum computing. We will represent as this. So, suppose the system has k classical states, then you will just write it as a superposition using complex numbers. And if you have like 2 systems and you want to put them together, yeah, then you will take the tensor product, and yeah, they can be entangled or disentangled and so on, unentangled. Or, okay. Yeah, fine. So, given a quantum mechanical object, yeah, what can you do to it? What can you do to it? So, the thing is this, the mysterious thing about this quantum mechanics thing is, suppose you have a qubit in this state, yeah, this is a way of only representing the state. You will never be able to figure out what alpha 0 and alpha 1 is. The object is in that complex combination state, but you will, as a human beings, we cannot perceive complex numbers, we cannot find out the state alpha 0 and alpha 1. Yeah, we can only do one thing to the system. Yeah, we can do what is called measurements. Okay, we can measure the system. Okay, so what is measurements? So, yeah, so the simple type of measurement, yeah, one can do is called the standard measurement. Yeah, measurement in the standard basis. So, suppose you have a quantum mechanical state alpha 0 0 plus alpha 1 1. Yeah. So, you can measure in what is called the standard basis. Yeah. So, measurement is nothing but a matrix multiplication. Okay. So, yeah, so yeah, so this is what is called the bracket notation. So, I have been using this kind of notation everywhere. This is called what is called the bracket notation. Yeah, it was invented by physicists and it is very useful. I think this is by Dirac. Yeah, Dirac invented this notation and they are very useful somehow. Okay, it is very easy to manipulate this and do things. So, in Dirac notation, yeah, the two measurements that you can do is basically what this means is okay, essentially these two matrices. Yeah, essentially you basically multiply the vector by these two matrices. Yeah. So, what is this matrix doing to this vector? Yeah, so, what is 0 0 doing? Yeah, suppose you, so this is this particular matrix and you are multiplying it by alpha 0 0 plus alpha 1 1. What will happen? What will you get?
So we get alpha 0 times 0.
So, you will get alpha 0 times 0. Okay. So, if you also actually symbolically manipulate, you will get the same result. So, this thing is nothing but, yeah. So, you will have so the scalar comes out and you will have alpha 0, yeah, 0 and yeah, I am taking just the scalar out and just moving in the rest of the thing. Yeah. I am just taking the scalar out and moving the rest of the thing in. Yeah. So, this thing when you have something like this, yeah, I mean, yeah, this is essentially doing a dot product. Yeah, this is essentially doing a dot product. And 0 dot product with 0 is actually 1 and 0 dot product with 1 is actually 0. Yeah. So, you will get alpha 0 0. Is that clear? Okay. Yeah. So, I mean yeah. So, if you apply this measurement, you will get alpha 0 0. Yeah, and you do not actually see alpha 0 0. What you will see is the absolute value of alpha 0. Yeah, sorry, you will take the absolute value of the complex numbers. That's what you are observing. Okay. actually I should be little more careful. Yeah. When you do the measurement, you cannot choose these matrices. Yeah. A measurement is a set of matrices. Yeah. So, a measurement is a set of matrices. Yeah. And if you apply the 0 0 matrix, you will get you will get the state 0 with the probability alpha 0 square. Okay. With the probability alpha 0 square, you will get 0, and with probability alpha 1 squared, you will get the state 1. Okay. So, when you do a measurement, in the end you will observe a classical state. Okay. You have no way of observing a quantum mechanical state. As human beings, we cannot perceive quantum mechanical states. Okay. We can only perceive classical states. The system is in some superposed state, and when we do the measurements, so a measurement will be a set of matrices, and if you so basically you do the measurement, with alpha 0 square probability, I will see the state 0, and alpha 1 square probability, I will see the state 1. This is what you can observe. Okay. So, basically the output would be randomized, and depending on alpha 0 and alpha 1, the probabilities vary. And after you have observed 0, the state of the system will become 0. So, initially the system was at this state, we had alpha 0 0 and alpha 1 1. You do this measurement on this system, you do this measurement, measurement is a set of matrices, it is a set of matrices. You will see a 0 1 0 with some probability, 1 with some probability. We do not know what that probability is, but you will either observe 0 or 1. It is with alpha 0 square probability I will see 0, alpha 1 square probability you will see 1. And after the measurement, the system also changes. This state gets destroyed. After the measurement, the state of the system gets destroyed. And if you observed a 0, the state will also become 0. If you observed 1, similarly, observe 1, you will see the state of the system will be 1 after that. So, this is the dangerous thing of quantum mechanics. You cannot observe what is really the system is in. You have a look at it, you will get some answer, and the state of the system also changes. So, this is very much related to your Heisenberg uncertainty principle. Okay. So, you cannot simply passively observe things. You observe things, the state of the system also changes. You will get some information out of the system, but then the state of the system also changes. Okay. And so we can interact with a quantum mechanical system in very limited ways. We can do this measurements, and this it will and you will get a results with some probability, and the state of the system changes after the measurement. So, one important consequence of this is this alpha 0 squared plus beta 0 squared has to be alpha 1 squared has to be equal to 1. So, the sum of absolute values of amplitudes has to be equal to 1. Of absolute values of amplitudes, this is equal to summation over I alpha I squared has to be equal to 1. Take any quantum mechanical system, yeah, if alpha are the amplitudes of the different classical states, the sum of squares of absolute values has to be equal to 1. Okay. Any questions? Okay. So, let us see some examples, okay, that will make it more clear and yeah, will get you comfortable. So, yeah. So, let us say you have a 2 qubit system. Let us say you have a 2 qubit system. Yeah. So, yeah, let us say you have this system itself. Okay. So, you have this alpha 0 0 plus alpha 1 1. Yeah. So, instead of measuring in the standard basis, I am going to measure in a different basis. Okay. So, my new basis is the following. Just a second. Yeah. So, I am calling this new basis as plus, which is 1 by root 2 0 plus 1, and yeah. So, I am defining some new basis, yeah, which is plus and minus basis. Okay. So, are these orthonormal? Are these orthonormal?
Yes.
Yes, because if you take the dot product, it is 0, and if you take the dot product with itself, it is 1, right. Yeah. So, these are orthonormal bases, and I want to measure according to this particular matrices. So, I will do plus plus and minus minus. Yeah. So, I am doing a measurement. Yeah, this is the measurement operator, they call this the measurement operator. Yeah. So, could you tell me what the probabilities of getting the plus outcome or the minus outcome? Yeah. So, earlier you had this state, and you had the measurement operator was this, yeah, and you got the 0th outcome, yeah, with probability alpha 0 squared, and the 1th outcome with probability alpha 1 squared, yeah, absolute values of alpha 1. Yeah. So, now we change the measurement operator, yeah, it is another basis vector. Yeah. So, how do we yeah, I mean, what is the outcome of the measurement? How do we find out? Yeah. How do you approach this problem?
Do the dot.
Sorry.
So we can sort of try to convert alpha 0 plus alpha 0 0 plus alpha 1 1 into the new plus minus basis.
Yes. Yeah, you will change the basis. Yeah, you will convert this problem to that problem by changing this representation to the new plus minus basis. Yeah. So, if you look at it, 0 is actually plus plus minus, yeah, then the 1 cancels out, and then what should I do? There is a 1 by root 2 or something sitting there, yeah. So, I should also do
Divide by 1 by root 2.
yeah, okay. Similarly, 1 is basically equal to plus minus minus, okay, 1 divided by root 2. Yeah. So, we can substitute, and what will you get? So, the state, let us say this is the state phi. Now, phi in the new basis is how much? So, yeah, so there will be alpha 0 by root 2 and alpha 1 by root 2, plus 0 plus alpha 1 divided by root 2 of plus, yeah, and alpha 0 minus alpha 1 by root 2 of minus. You agree? Yeah. So, we change the basis for, yeah, representing the system, yeah, and then you measure according to this measurement, and what will you get? What is the probability of state 0? State plus, sorry. Now, you are in the plus minus basis. So, what is the probability of getting the state plus?
It could be alpha 0 plus alpha 1 by root 2 whole square, the absolute value of that whole square.
Yeah. Okay, and similarly, the probability of state minus is alpha 0 minus alpha 1 by root 2 the whole square. Yeah, does these two sum up to 1? I hope so. Yeah, I think they sum up to 1. Yeah. Okay. Yeah. So, just an exercise. Yeah. Okay. So, yeah, measurement operator are typically they are yeah, these kind of projection to mean one of the bases. So, you will have some orthonormal basis and you are going to projecting to each of the bases, yeah, and it need not be the standard basis, you could have other bases as well. Okay. So, you could have more general projection operators, okay, measurement operators, yeah, more general measurement operators. For example, let us say you have this particular state, yeah. So, you have alpha times 0 0 plus beta times 1 1. Yeah, this is yeah, a 2 qubit system and it is in this entangled state, yeah, and you can measure only the first qubit. Yeah, what do I mean by measure only the first qubit? Basically, the matrix we are interested in is 0 0. Yeah, you are measuring the first qubit, tensor product the identity matrix, the 2 by 2 identity matrix, yeah, and 1 1 tensor product 2 by 2 identity matrix. Yeah. So, you are not touching the second qubit, you are just touching the yeah, I mean first qubit and doing this measurement. So, let us look at a general 2 qubit system. So, let us talk about alpha 0 0 0 0 plus alpha 1 0 1 0 plus alpha 0 1 0 1 plus alpha 1 1 1 1, yeah, and you are measuring according to this particular measurement. Yeah. So, what is the outcome? Yeah. Yeah, so just a second, I am also a little bit confused here. So, what do you think the outcome would be? Yeah. So, if you apply this operator, yeah, if you apply this operator to this, yeah, what you will get? So, you will get if the first qubit is 1, you will get 0 if you apply this operator, right. So, you will get alpha 0 0, yeah, into 0 0 plus. So, this if you take a product with this, it will become it will become 0, because the first qubit is 1 and the first qubit is 0 here, yeah. So, they are orthogonal, yeah. This and this you can take a product. So, this will become alpha 0 1 into 0 1. The second bit is unaffected because you are multiplying with identity matrix, yeah. So, you will get this particular state, yeah. And since you have to normalize things, yeah. So, the new state would be so if this when you apply this measurement, if this outcome obtained, then the output state would be this, and if this outcome was obtained, then the output state would be alpha 1 0 1 0 plus alpha 1 1 1 1 divided by yeah. So, okay. So, so you will get these two outcomes. I mean, if this outcome was obtained, the state would be this, and this outcome was obtained, the state would be this, and the probability of this outcome would be this outcome would be okay. Yeah. So, here you are measuring only the first qubit, yeah, part of a entangled 2 qubit system, yeah, and you will get the 0 outcome for the first qubit, yeah, with probability alpha 0 0 squared plus alpha 0 1 squared, yeah, and after the measurement, the state of the system would be this. Yeah, I mean, if you saw the 0 outcome, then the state of the system would be this. Now, you will also get the outcome 1 with probability 1 alpha 0 1 squared plus alpha 1 1 squared, and after the measurement happened, the state of the system will become this. Okay. So, yeah, this is the state after the outcome, and this is the probability, yeah. And so this is for outcome 0 and this is for outcome 1. Is that clear? Is there a question? Yeah. So, when you have a 2 qubit system, it can be entangled and there could be 4, yeah, complex numbers involved, and yeah. So, you have only 2 measurement matrices because yeah, you are only looking at the first qubit. Second qubit essentially is identity. I mean, the second qubit, the measurement matrix is identity, you are not touching it, and when you apply it, basically you will get these probabilities for the 2 outcomes, and the final output would be this. Yeah, I mean, the first qubit was observed as 0, but the second qubit could be 0 or 1. So, it is the remaining parts of the state, yeah, but you need to renormalize it because now you have observed that the first qubit is 0. Okay. Yeah, so, these are called more general projection measurements. Okay. These are more general measurements. Okay. So, now we have yeah, so we have described how to represent quantum states, yeah, and instead of bits you will have qubits, and qubits can be in this entangled state. Okay. Now, there is an interesting thing going on here. So, suppose we took that our special state that we saw earlier, it is 1 by root 2 0 0 plus 1 1. Okay. Suppose you took the state, yeah. Yes, suppose the first qubit, yeah, is with you and the second qubit is with me. Okay. So, yeah, so we prepared this, we were together sometime, and yeah, our qubits were entangled, yeah, and it was together in this particular state, yeah, and then you went away to a different planet, and I am sitting here, yeah, and but our qubits are entangled, yeah, our qubits are entangled according to this particular state, yeah. Now, let us say I measure my state, okay. Let us say I measure my state according to the, yeah, according to this particular measurement, yeah. So, suppose yeah, so I do this particular measurement to my state, I am only sitting here, I only have access to my state, I can do this measurement on my qubit, yeah. So, what will happen? What is the probability that I see 0?
It would be half.
Yeah. So, with probability 0, I see probability half, I see 0, yeah, and after the measurement the state would be, after the measurement the state would be
0 0.
0 0. Okay. The state of the combined system is 0 0. You are sitting in another planet, yeah, I am sitting here, I made a measurement on my qubit, yeah, and I got the outcomes 0 with probability half, okay, I observed 0, yeah. Now, the state of the combined system is 0 0, yeah, and suppose you do the measurement, yeah, 0 1 measurement at your side now, what is going to happen?
We will measure 0 with 1 probability.
You will measure 0 with 1 probability, yeah, but I did not touch your qubit, you are sitting in another planet, I did not touch your qubit, I only did measurement on my qubit, yeah. Somehow I made the measurement on my qubit and it influenced your qubit even though you are far away, yeah. Yeah. So, this Einstein called this, Einstein was very annoyed by this quantum mechanics, okay, and this particular state annoyed him a lot, okay. So, this particular state is called the EPR state, EPR or Bell state, okay. Yeah. So, this is Einstein, Podolsky and Rosen. Podolsky, Rosen. So, Einstein was very annoyed by this state because it meant that we can have two qubits, we can be together initially and we can entangle qubits according to this. I do something to my qubit and your qubit also responding to it, even if you are light years away, instantaneously. Yeah. I apply my measurement, instantaneously your qubit is also changing even if you are light years away, yeah. And this was weird for him because according to his own law you cannot travel faster than light, and here the information communication somehow is happening faster than light, instantaneous, okay. So, yeah, this Einstein called spooky action at a distance, I think Einstein only called it spooky action at a distance, and this kind of changed the worldview of physicists completely, right. I mean, you can have instantaneous things happening even faster than light, you can do some faster than light communication even, looks like in some sense. Yeah, you just need to entangle the qubits initially, and then you can go far away. Then I can yeah, somehow I do something to my qubit, and your qubits also respond. Yeah. And yeah, so we will come back to this particular state multiple times, and many algorithms use this kind of states. Yeah. So yeah, so this just observe this. So yeah, it's a important phenomenon that happens in quantum computing. Okay, so what else? Yeah. Okay, so now we have yeah, I mean described what yeah, qubits are, and yeah, how can we observe qubits. Yeah, physically we have only very limited way of observing qubits through these measurements. Yeah, and they have huge limitations. Yeah. Now what else can you do with qubits? Okay, if you are not doing measurements, yeah, only thing you can do is unitary evolution. Okay, you can do what is called a unitary operation. Yeah. Remember, in Turing machines, if you have bits, you do like simple operations, and or not and or you can do in bits. Yeah. So this unitary operation is like your and or not. Yeah, it is some operation that you can do on the qubits. Okay. So this a unitary operation is essentially a matrix. Okay. Suppose you have a two qubit system, it is essentially a matrix. Yeah. And yeah, the matrix kind of yeah, you need to take a product of the matrix and you will get some output state. Yeah. The important thing is this matrix is a orthonormal matrix. Yeah. No, not actually orthonormal, it is a Hermitian matrix. Okay. I mean, yeah, sorry, yeah, basically if you take this matrix U times U dagger. Yeah. So U dagger is U transpose complement. So remember, we are talking about complex numbers. This matrix can have complex values. Yeah. So if you take sorry, I should I am just confusing things. If you take the conjugate and the transpose of the matrix and you take the dot product, yeah, you will get the identity matrix. Yeah, so this is called a Hermitian property, I think. Just a second. No, this is called a unitary property. If a matrix satisfies this, it is called the unitary matrix. Okay. Yeah. So yeah. So basically, yeah, I mean this is actually equal to U inverse. So it is very easy to get the inverse of a matrix. Okay. So this is analogous to your orthonormal matrices. Yeah, when you have real numbers, when everything is a real number, then an orthonormal matrix is same as the unitary matrix. But when you have complex numbers also, you also need to take complements of the complex numbers. Okay, sorry, conjugates of the complex numbers. Okay, so this is kind of analog of orthonormal matrices, but to complex numbers. Okay, so these are unitary matrices, and you can yeah, transform a quantum state by a unitary operation, that you can do. Okay, you can transform a I mean yeah, quantum state by a unitary operation. The important thing is a unitary matrix is always invertible. Yeah. Okay. So all quantum computation is always reversible. That is, if you do a set of operations and you got a final state, yeah, from that final state you can actually recover the initial state, because there is always an inverse operation. Okay, so the computation is always reversible. Yeah, is this true in classical computing? suppose you have 2 bits, I take the AND of the 2 bits. Yeah, from the output, can you recover the input? You cannot, yeah, because yeah, I mean, if the output is 0, you don't know which of the bits was actually 0. Maybe both the bits were 0, maybe only one, the first one was 0, maybe the second one was 0. Yeah, but in quantum computing, that will never happen. All the operations that you do is going to be reversible. From the output, you can figure out the input also. Okay, so let's see some examples. Yeah, so yeah, so there is always the NOT gate. Yeah, so how do you implement a NOT gate as a unitary? So let's say you have you need to find a matrix U such that alpha 0 0 plus alpha 1 1. Yeah, the output of this is basically alpha 0 1 plus alpha 1 0. Now, what is the matrix U?
So it would be like 0 1 1 0.
So if you use this matrix, you have your this thing. So there's another interesting way of writing this matrix. Yeah, so yeah, so if you see a 1, you replace by a 0. I mean, so this is the bracket notation for it. Yeah. Yeah, I mean, basically if you apply this matrix to here and you use the dot product, you will exactly you will get the thing. Yeah, so this is equivalent to this in the bracket world. Okay, okay, so yeah, so we have the NOT operation. Yeah, so what else can we do? What other thing can we do? There are some basic gates, just like in classical computing you have AND or NOT. Okay, you can implement any gates using these 3 gates. Yeah, you can have a set of universal gates, yeah, which can implement any unitary transformation. Okay, so I mean, yeah, so yeah, so there are actually 4 operations. So I is the identity operation. This is again a unitary operation, does not change the state at all. So X is basically the flip operation, which is just what we described now. And there is something called the Y operation, which is yeah, so let me just describe the Z operation now. Yeah, so Z operation is basically what is called a phase shift operation. So what it does is it will give a minus to mean the second coordinate. Yeah, so Z times alpha 0 0 plus alpha 1 1 excuse me. Yeah, so it just negate the second complex number in the state. That's what the Z operation does. So there is one more important operation, called the Hadamard gate. Okay. So H or the Hadamard operation. So basically the matrix is basically, it's a weird matrix. Okay, you initially you will not understand what is happening, but this is extremely useful. it's a matrix like this, 1 by root 2, 1 1 1 minus 1. Yeah. So what happens if I apply H to the 0 vector?
It will become 0 plus 1 by root 2.
Yeah, so this becomes the plus operator. If you remember, initially we had this plus basis. Yeah. Similarly, if you H apply to the 1, you will get the minus. Yeah. Okay. So yeah, so this is the Hadamard operation. Yeah. Yeah. So there is another interesting operation which is called the C naught operation. Okay. So these are all 1 qubit operation. Yeah, the single bit you can do this operation. Yeah, C naught is a 2 qubit operation. So what should be the dimension of the C naught matrix? It's a 2 qubit operation, it acts on 2 qubits. So what should be the
So it should have size 4 by 4.
yeah, it's a matrix of size 4 by 4. Okay, so I should make a 4 by 4 matrix. Instead, I will just give you 2 rules from which that 4 by 4 matrix will be obvious. Yeah, so C naught, yeah, of 0 B. Yeah, so 0 is the first bit and B is the second bit. B can be 0 or 1. Yeah, this is going to be equal to 0 B only. Yeah, and C naught of 1 B is going to be, yeah, 1 B bar. Yeah. So what it does is, yeah, based on the first bit it will flip the second bit. If the first bit is 0, then it does nothing. Yeah. If the first bit is 1, then it will flip the second bit. Okay. Yeah. So yeah, what when C naught is applied to, let's say, alpha 0 0 0 0 plus alpha 1 0 1 0 plus alpha 0 1 0 1 plus alpha 1 1 1 1, what happens? C naught is applied to this gate. Yeah. So what will happen? What is the final output? So nothing happens here because yeah, I mean the first bit is 0. Yeah. So here the first bit is 1, so it will flip the second bit. Yeah. And what happens here? It won't have, there won't be, it won't touch it because the first bit is 0. And what happens to this? Here the first bit is 1, it will flip the second bit. Yeah. So is that clear what happens? So that's the C naught operation. So it's a good idea to write down the matrix of the C naught. Yeah, that I guess I will leave it as an exercise. Yeah. Yeah. Okay, so we have introduced enough matrices. Yeah, and let's try to solve one problem. Okay. Okay. So let's say so this problem is called quantum teleportation. Okay, for some reason it's called quantum teleportation. So the problem is this. Okay, now I have, okay, a qubit, okay, in a state alpha 0 0 plus alpha 1 1. Okay, I have a qubit sitting in this particular state. Yeah, and I want to give you this qubit. I want to give this qubit to you. Yeah, is there any way I can give this qubit to you at this particular state? there is no way, even I do not know what alpha 0 and alpha 1 is. Yeah, I mean it is in some unknown state. I have a particle in some unknown state. I mean I do not even know what alpha 0 and alpha 1 is. I can only do measurements, in which case the state of the system also changes. Yeah, so I cannot I mean give you this qubit just like that. It's no easy, and you are also sitting, let's say, far away. Okay, but let's say both of us has a EPR state. Okay, we have another qubit. Yeah, we have another 2 qubits sitting in the EPR state. Okay, so yeah, so there are actually 3 qubits. Yeah, so I mean I have this 1 qubit. Yeah, and I also have 2 other qubits which is in a EPR state. Sorry, I mean okay, so just a second, I'm just confusing. So let's call the 2 parties A and B. Yeah, so A has 1 qubit in this particular state. Yeah, and A has another particular qubit, and B has another particular qubit. These two are entangled. Yeah, and these two together are in 0 0 plus 1 1 1 divided by root 2. Yeah. So yeah, when we were together earlier, and yeah, we kind of have a state which is in this entangled state. Yeah, and now I got a new state. Yeah, alpha. So this particular phi I got, and I want to send this state to you using your EPR state. Question is it possible? Okay, so yeah, so essentially I am teleporting my state to your state. Yeah, so how do you do it? So the way to do it is, before going into it, we should have an interesting way of representing these. Okay, so the way you represent these is basically by doing lines. Okay, so there is a phi here. Okay, phi is with me only. Yeah, so there is the A part and the B part. Yeah, and then there is these two particular states. Yeah, this is in entangled. So this is in 0 0 plus 1 1 by 2. Yeah, so these two states are I mean actually these two states are not shared, but yeah, so these two are with A and this is with B. Yeah, so these two qubits are with A and this is with B. Yeah, so what Alice will do, yeah, to teleport her state to other, yeah, is going to be the following. Yeah, so first you will perform the C naught operation. Yeah, so yeah, so basically here you will perform what is the C naught operation. Yeah, and so you will have the C naught operation, yeah, and followed by the Hadamard operation. Yeah, so just a second. Yeah, so the interesting thing is, after doing this, yeah, even if you are, let's say, A and B are far away, after doing this, yeah, the bth qubit, yeah, will have exactly the state phi. Yeah, so yeah, I mean even if yeah, I mean yeah, so the b's qubit will have exactly the same state as phi. Okay, so I will explain this in the next lecture. Okay, yeah. So yeah, so this uses kind of this EPR state to copy the state even if you are far away. Okay, you can copy a state that is only there on one side to the other side. Okay, okay, so yeah, I think I will end here for today. Okay, so yeah, it takes some time to get used to these things. Okay, I will describe the teleportation, yeah, I mean yeah, logic in next time. Yeah. Okay, so yeah, let's just review what we did and stop here. Okay, so we described the principle of superposition. Yeah, that is yeah, a quantum computing state can be a superposition of many classical state, and superposition is by complex numbers. Okay, and so you also saw qubits. Yeah, a qubits could be unentangled or entangled. Yeah, so yeah, unentangled is tensor products of two independent states. Entangled is there are certain states which are like yeah, they are highly entangled, they are highly correlated. Yeah, they cannot be written independently. Yeah, that's an entangled state. Yeah, and we also looked at measurements. Yeah, so you could measure in the standard basis or some other basis. Yeah, and when you measure, you will get a outcome with some probability. Yeah, depending upon the complex numbers alpha 0, alpha 1. Yeah. And after the measurement, the state of the system changes. It collapses to one of 0 or 1. Yeah. So yeah. Okay. And we also saw in general projective measurements. Yeah, you could measure only one qubit. Yeah, if you have a multiple qubit system, you could measure only one qubit. Yeah, in which case, yeah, I mean, yeah, so you could have a 2 qubit system in this particular state. Yeah, and if you measure only the first qubit, yeah, I mean the outcome could be 0 or 1, and the probabilities is going to be sum of squares of complex numbers with that particular bit equal to that. Yeah, and here it will be equal to 1. And you need to renormalize the state with those particular state vectors. Yeah, and yeah, so this will be the after the measurement, this will be the state of I mean according to these two matrices, which what the outcome of the measurement was. Okay, and yeah, if you are not doing measurement, you can do unitary operations to qubits. Okay, so what is a unitary operation? So unitary matrix is any matrix such that yeah, the inverse of the matrix is essentially the complement transpose. Yeah. And yeah, so this meant that all operations are reversible. Yeah. So all quantum operations will be reversible, unlike in a classical computing world. Okay, and one important consequence of this is yeah, so we will come to it in a minute. So you cannot implement the AND gates in the usual way, because AND gates will lose information. They are not reversible functions. Yeah. Also, we looked at a few yeah, I mean unitary operations. Yeah. Okay. We looked at the Hadamard operation. We looked at the C0 operation. Yeah. And yeah, I just explained what quantum teleportation is, but I will do that again in the next lecture. Okay. So if there are any questions, I can take now. Yeah, so that's all for today. We just I mean gave out some definitions and so on. Yeah, so from tomorrow we will start looking at yeah, I mean what are called quantum circuits. Yeah, and quantum circuit which actually solve some problems. Okay, yeah. So in fact there is a particular problem called a search algorithm which can search through 2 raised to n length arrays. arrays of length 2 raised to n, and find an answer. So, in classical computing this problem will take 2 raised to n exponential time. And in quantum computer, yeah, we can show that that particular problem has a polynomial time algorithm. Yeah, so you will see one example problem where in fact quantum computing is exponentially faster than classical computing. Yeah. Also we will look at we will try to go over so there are a couple of other algorithms, quantum algorithms also, the basic quantum algorithms which we will go over. Yeah. So we will have 2 or 3 lectures on it, and yeah, that hopefully will get a good idea of what quantum computing is. Okay, so if there are no questions, I will end the lecture. Okay, then bye.